So let's go ahead and take a look at the simple case. Suppose we let B equal 0. That is, suppose there is no damping force. This absence of damping force means there is an overall absence of friction of any sort. Now we're going to, going forward for a little while, we're going to assume there's no forcing function. We're going to focus on the homogeneous case. And if we let B equal 0 and we let K equal 1 and M equal 1, you can see that here we'll have the second derivative plus 0 over 1 times y prime, so that term goes away, plus 1 over 1 times y equals 0. So that's why this coefficient is a 1 here. This is the k over the m, the 1 over the 1, which is 1. Now we've already solved this equation. We already know that there are two solutions that will work. y1 equals sine of t, and y2 equals cosine t. Perfect. So now we have two separate solutions, but we really need to know what to do with them. In order to understand what to do with them, we use what's called the superposition theorem. The superposition is kind of like when you superimpose an image over another one. It makes it look like you can put somebody in a different background. Excuse me. So if I take a picture of myself and I put it, kind of Photoshop me into a situation where I'm in Disneyland, but I'm not really there, that's called superimposing, but superposition is very similar to that in concept. So given a homogeneous differential equation, which includes but is not limited to the spring mass system, if two linearly independent solutions can be found, right now don't worry about what that means, linearly independent means that they're not just multiples of one another. So cosine and sine are two entirely different functions. So if you can find two solutions, y1 and y2, then any linear combination is also a solution. Y of t equals some multiple of y1 plus some multiple of y2. These guys here we have two arbitrary constants. And just to provide insight into this, according to our solution, our general solution would be k1 sine of t plus k2 cosine t. And how do we know that that's a solution to this equation? Well, we'd have to compute its second derivative, which would be, let's see, k1 sine of t, its derivative would be k1 cosine t. And remember, k1 and k2 are just constants. Minus k2 sine of t. And if we take the derivative of that, k1 cosine of t, its derivative is negative k1 sine of t. And the derivative of k2 sine t is minus k2 cosine t. And if you add these together, what should they give us? Well, if we add the second derivative to y, they should cancel out and give us 0. And these two added together, negative k1 sine t plus k1 sine t. Negative k2 cosine t plus k2 cosine t, they cancel out and give us 0. So y double prime plus y does in fact equal 0. So that's how we know that's a solution. So superposition really just puts two solutions, smashes them together. And the reason this really works is just because you're adding. When you're adding and you're dealing with derivatives, the derivative is a linear operator. So it takes the derivative of each term in the same way. Given no damping, what is the general solution? So our general solution, we just said, was any multiple of sine t plus any multiple of cosine t. Now, the reason we have two arbitrary constants is because we have one, this is our initial position, and also, so if you pressed play on the image, you would not only see that spring mass system stuck at a certain point, but the second you press play, it would start to move. And therefore, it's going to also have to have an initial velocity. So let's think about what's going on here in this picture. So we have some spring mass system, and it doesn't matter where we draw it. Now I'll draw it vertically this time. So here I have some mass attached to it. Now it's not at rest. Its initial position at time 0 is 1 unit of stretch. Remember, we said that positive will mean that it is stretched. So this distance from here to here is 1. And because we are in the metric system, that's going to be 1 meter. Also, y prime of 0 equals 2. It's a positive number, which means it is going to continue stretching. So when we press play, that spring mass system is going to continue moving downwards. So how do we actually work with these two initial conditions? Well, the first one is a value of the position, and this is my position function. This initial velocity is a value of the velocity function, which is the first derivative of position. So in order to solve for the constants, I actually have to find the velocity function, which we said was k1 cosine t minus k2 sine t. And this is our velocity. Right? So once we have the solution for position, we can take derivatives all day long. And now we're going to make the substitution. Here we said the initial position for the position function. The initial position function will have a value of y when t is 0. And equation 2, the velocity, will be positive 2. k1 cosine of 0 minus k2 sine of 0. Okay, so we have a system of equations to solve. The good news here is that sine of 0 is 0. So that will be 0. This will be 0. And cosine of 0 is 1. And cosine of 0 is 1 there as well. So the two equations that we actually get are 1 equals k2. And the second one says 2 equals k1. So our final solution for our particular solution for this model is going to be y equals 2 sine t plus 1 cosine t. And let's just go ahead and take a look at this in Desmos to see what's going on. So here we have the solution, 2 sine x plus cosine x. And remember, one thing that we want to note here is the x-axis is time, and this is going to be measured in seconds. The y-axis is position from rest, measured in meters. And so one thing that we want to just verify in this solution is what's the initial condition? Well, initially the mass or the spring is stretched by 1 unit. Y equals 0 represents the equilibrium or the rest position of the spring. We also see that the spring is, now we can't actually compute, we can check that the second derivative, or that the initial velocity is 2, but definitely we describe that the spring mass system is stretching. Now I'm going to do something cool here. I'm going to insert a slider for time, and I'm going to set time to go from 0 to 12 seconds. So what I'm going to do here is I am actually going to plot a point, and I'm going to plot the point 0, and let me call this function here f of x equals. So what I'll plot is 0, f of t. Now all that's doing is that's going to show me a point on the vertical axis, so that the t value is not going to change, but the y value is going to be the current value of where that spring is. So what this is going to do, and I'm going to slow this down a bit and have it just do it one time. So watch what happens. So if you watch this green dot, that's just describing, that's basically the spring mass system oscillating up and down. So now it's going to, at first it goes to a stretch, it goes into a stretch, rest, compression, rest, stretch, rest, compression, rest, and so on. Now one thing that we should notice is that we would ideally like the spring mass system to come to a stop, but we've assumed no damping. That is, we have no friction, we have no gravitational pull, and that's why this is what's happening. Now, another thing I could have done is I could have just plotted the point t f of t. So watch this. Now we'll have both the green and the purple dot moving. The purple dot is actually following the curve, but the green dot is just keeping track of the vertical position of that purple point. So that becomes a very handy tool to have. So let's suppose that we just adjusted our system a little bit, and we said that let k equal 8. Now from our spring mass system, the second derivative plus b over m times the first derivative plus k over m times y equals 0. And we've just said b equals 0, so this whole term will go away, because 0 over 1 will be 0. And so we'll be left with the second derivative plus 8 over 1, which will just be 8y equals 0. Now we've already kind of described how the solution changes the input, and we can verify this. For sine is going to be the sine of the square root of 8t. And the reason that's going to work is because when you take its second derivative, the square root of 8, two multiples of that will come out, and you'll have 8, negative 8 sine of the square root of 8t. And if you take the second derivative, negative 8 sine square root 8t, plus 8 times positive sine square root 8t, they cancel out and give us 0. Also, y2 equals cosine of square root of 8t. That's also going to work. And for the same reason, now our general solution is going to be any multiple of the first, which is sine square root of 8t, plus any multiple of the second, cosine of square root of 8t. Now for our initial conditions, we're going to need the velocity function. So the first derivative of this solution is going to be square root of 8 k1 cosine of the square root of 8t. And that's going to be because of the chain rule. And then I'll have the derivative of k2 cosine square root of 8t will be negative square root of 8 k2 sine of square root of 8t. And now again, I'll plug in my initial condition. For my position, it is 1 equals, now the first term is going to be k1 sine of 0, which is just 0, plus k2 cosine of 0, which is just 1. For the second equation, y prime, so that's going to, y prime is 2 at time 0. Square root of 8 k1 cosine of 0 is 1, so square root of 8 k1 times 1, which is just square root of 8 k1, minus, this is going to be 0 because sine of 0 is 0, and so this leads to giving me a k1 of 2 over the square root of 8. So my general solution, or my particular solution for this set of initial conditions, is going to be y equals, we said 2 over the square root of 8. And you can leave it like that. No need to reduce this down or rationalize denominators. We'll leave it like that. And then plus our k2, which is 1 cosine of the square root of 8t. So let's go ahead and compare our solutions. And so now we have 2 divided by the square root of 8 times the sine of square root 8x plus 1 cosine of square root 8x. And just double checking that. That's what we should have. And one of the things you notice right away is, first of all, the initial conditions are both the same for the only thing that's changed here is the spring constant. Here we made the spring kind of stiffer, and one thing that we should note is if you have a very loose spring, relatively speaking, this very loose spring kind of just wobbled up and down very slowly, but now that we've put in a higher spring constant, this thing oscillates much more rapidly. So that's the effect of having a stiffer spring, is that don't go out and try this, but if you take the spring in a mechanical pencil, let's say, and you squish it and you let it go, it kind of wobbles a little bit, right? And doesn't do it very rapidly. But if you were to push on the hood of a car really quickly, you would feel the car oscillate very quickly and come to a rest. So one thing we see here is that it's oscillating a lot faster. It completes one full oscillation in 2.2 seconds, whereas here we completed one full oscillation after 5.82, no, not 5.82, excuse me, from peak to peak, that's going to be 2 pi, all right, because in this case, our period is going to be 2 pi over the coefficient, so period equals 2 pi over 1, so it's going to be 2 pi units from peak to peak. Here, our argument is square root of 8, and what that means is that, what I'm trying to say here is that if we write period, oh, this is not working very well. Let's try it over here. So yeah, so period, for if you have sine of bt like that, then the period is equal to 2 pi over b. And its units are seconds. So that's how many seconds it takes to complete one oscillation. So if b is square root of 8, then this is going to have period equal to 2 pi over the square root of 8 seconds. Now that comes out to approximately 2 pi divided by square root of 8 to about 2.22 seconds. 2.22 seconds. Back up when we had our previous one, our period was 2 pi over 1, which took about 6.14 seconds. So if we take a look at the comparison, and let me call this second function here, I'm going to remove this one, we don't need that anymore. Just so you can see them oscillate, we'll call this function g of x equals, and we'll plot the point 0, comma g of t. So all that's going to do is, now watch the red point and the green point, you're going to see the red point move up and down a lot faster. So you see the green point's taking its sweet time. It's taking about 6.2 seconds, 6.3 seconds to complete an oscillation. For the green one, it's taking a lot less time. It's taking about 2.22 seconds.